Hi, this video is part 3 of a mini-series based on a new research paper released by Anthropic in March 2025. They are the company behind the Claude language models, and in this study, they did something few research teams have done. They've opened up the black box. They used a method called circuit tracing to investigate what's happening inside their model Claude, not just when it gives a right answer, but when it makes a mistake, especially the kind we're all familiar with, hallucinations. Hallucinations happen when a language model makes something up, an incorrect answer, a made up quote, a false claim. And this research gives us new insight into why this happens. In this video, I'll walk you through how circuit tracing helped researchers uncover the internal mechanism that controls when the model chooses to answer a factual question and when it chooses to say, I don't know. So let's start with the core observation from the paper. The researchers discovered that Claude has a dedicated internal mechanism, what they call a circuit, that helps it decide whether to answer a factual question or refuse. They call this the known answer versus cannot answer circuit. To study it, they used a very straightforward example. Michael Jordan plays the sport of. The correct answer is, of course, basketball, and the model gives that. But the key question is, how did it get there? Using circuit tracing, the researchers identified two main pathways in the model's internal graph. A syntactic pathway that processes the structure of the sentence, like recognizing that X plays the sport of Y. That's a familiar construction. And a semantic or factual pathway that connects the token Michael Jordan to known language, specifically basketball. What they found is that in cases where the model recognizes the name as familiar, a set of internal features they call known answer features become active. These features suppress another group, the can't answer features. This makes sense. If the model is confident, it knows who Michael Jordan is, it pushes down the I don't know signals and proceeds with an answer. But the interesting and important part comes when the confidence is misplaced. Sometimes the model sees a name or a term that partially overlaps with known entities. It might have seen it once or twice, or it just resembles other known names. When that happens, the known answer features can activate even though the model doesn't have a solid factual knowledge to support an answer. This misactivation suppresses the can't answer features, and that's what leads to a hallucination. I know, that's complicated. Let me give it to you in other words. The model thinks it knows something, but it doesn't. The wrong circuit fires, and the model gives a confident but wrong response. And here's where circuit tracing becomes incredibly powerful. By tracing these internal feature activations, the researchers could visualize the exact path that led from the input to the output. They saw that in hallucination cases, the known answer path misfires and the uncertainty signal is weakened or suppressed. Even more interesting, they tested this experimentally by manipulating the graph. They were able to reduce the activation of the known answer features or increase the influence of the can't answer features. And what happened? The model stopped hallucinating. Instead of giving a wrong answer, it said something like, I'm not sure, or simply didn't attempt to answer at all. This shows that hallucinations in factual questions are not random errors. They come from a specific and traceable failure mode inside the model where one internal decision pathway outweighs the other. The paper also makes a broader point. This known answer versus cannot answer circuit may be an instance of a more general decision-making mechanism in the model. It's part of how the model balances confidence with uncertainty. So, what's the big takeaway? Hallucinations don't come from missing data or bad training alone. They come from specific internal circuits misfiring, circuits that we can now trace, study, and potentially fix. By using circuit tracing, researchers are getting a much clearer picture of how these models make decisions, and more importantly, how those decisions can go wrong. Not from malice, not from confusion, but from misbalance between internal belief and internal doubt. This is a huge step forward in making these systems more trustworthy, because if we can understand the cause of a hallucination at the feature level, we can build better systems that can catch them early before they reach the end user. In the next episode, we'll take this a step further. What happens when a model faces not just a factual question, but a harmful request? How do refusal mechanisms work? And are they part of a model's training or something it develops through fine-tuning? And what happens when someone tries to jailbreak the model and override those safety features? That's what we'll look at in episode 4. See you then.